today we have Michiel van de Panne. We are very pleased to have him. Michiel is a professor of computer science at the University of British Columbia, UBC. He co-founded the ACM Zgraph Eurographic Symposium on Computers Animation, and also serves as an associate editor of ACM Transactions on Graphics. He's the recipient of the 2016 CHCCS Achievement Award for contributions to computer graphics in Canada. He and his group have been doing very great work. I've been always impressed with their work on motion planning, robotics, and machine learning, especially using deep reinforcement learning. So we are looking forward to your talk, Michiel.
Okay, great. I really appreciate the introduction and also for organizing the workshop. I think it's a fantastic topic, and given all the recent advances in model predictive control and reinforcement learning, and just a lot of exciting things happening with legged robots currently. I will not be watching the chat. So if someone else can monitor the chat and or just feel free to interrupt me with questions, that would be great. And yeah, so I come a little bit more originally from I've got always alternated between working on both robotics and animation, and so I tend to live in both of these worlds. And so given the recent more common use of simulation in designing motions for robots, then this is also translating fairly well to current work in robot design. But let me just first get started by acknowledging just all of my collaborators for the pieces of work that I'm about to show. And so I'll be more or less just summarizing all of their hard work. So having said that, this is the cliche video of many of the types of motions that we'd like to be able to create and that we can't yet create with robots. And so the question is, as I think Mark Rabert likes to say, how can we embody creatures and robots with athletic intelligence? I'll start by just briefly framing locomotion in a very broad sense, and in a way that I think may be more important over the coming months and years, in that there is not just one locomotion problem. There's really an entire spectrum, and typically, all of us we start with a canonical locomotion problem where perhaps the goal is to walk at a fixed speed forward in a straight line on flat terrain, and to build a controller where you have full access to the state information of the robot. And I think that's always the starting point for any kind of locomotion endeavor. And then of course where we want to end up is in the open-ended version. So here we can have variable terrain geometry, compliant terrain, different terrain frictions, rapid turns and jumps, working from sensory streams, so egocentric cameras that are just placed on our robot. And yeah, being able to do highly dynamic motions, and also to be able to deal with uncertainty. So we might not have full direct access to the actual state of the robot, or certainly the state of the environment. And this is maybe the biggest distinction between canonical and open-ended relates to in the canonical case, the state of the world or your system is the state of the robot, but in the open-ended version, the state really is some combination of the state of your robot and the state of the world, and the state of the world is just a lot less predictable than the state of the robot. But nevertheless, so progress is being made, and so hopefully I hope to touch on a variety of ideas that might be helpful in moving from canonical to more open-ended work. So I thought I would include this slide as a starting point, because whenever we're working on our own methods, we have our favorite set of tools that we like to use. And so here I'm casting it as, the MPC versus reinforcement learning boxing match. I hope to convince you that it should really be much more of a collaborative endeavor between model predictive control and reinforcement learning. And in the end, they really share a lot of issues. And in the end, we really need features of both of these methods. And so let me see if I can convince you of that. So I'll just quickly start off by giving you my cartoon sketch or caricature of model predictive control and reinforcement learning. And so if these are state spaces in model predictive control, you find yourself at some particular state, then, we can view a model predictive control as providing us with some kind of flashlight that can look some given horizon length h into the future, and then optimize some time index trajectory over that fixed horizon length. And so we'll optimize both states and actions typically over that finite window. Then once we've actually taken our action, then we move on to the next state. So shown by the hollow red circle, and the process repeats. And so we turn on our flashlight again and begin to re-optimize. So the hammer of choice here in terms of the underlying algorithms are typically some version of non-linear programming, although there exist many other variations as well of using cross entropy methods or other methods, population-based methods as well. But so over in the reinforcement learning world, we shift all our computation to be offline, and so conceptually we have some region of state space for where we pre-compute what our control actions are. And so then the nice thing is, if you find yourself in some given state, great, we simply use our policy to immediately look up what the control solution should be. So the advantage is, here the online computation you need to do is very minimal, because it's effectively some form of lookup, and the tools of choice to make this optimization framework work on the RL side are we need some kind of flexible representation of the policy and a value function. And so these are, we need flexible parameterizations of those. So commonly done with neural nets today. And then again, we need an optimization method. And so typically some form of gradient method for the policy. And okay, so that's my cartoon caricature of that. So just to summarize kind of the characteristics of these. So in over on the MPC side, we have online compute versus on the reinforcement learning side, we've pre-computed, and so we're really just doing some form of online lookup. Now, an advantage of over on the model predictive control side is we are in effect doing planning, and so if there's some configuration of the world that you've never seen before, then it's more likely that a planning process can successfully deal with that than a purely reactive method of dealing with it, which is what we have over on the reinforcement learning side. I actually like to relate this a bit to Daniel Kahneman's System 1 and System 2 of how humans deal with problems. And so where System 1 is effectively some kind of reactive immediate response that's informed by all kinds of biases, but it's fast, and so speed is important in responding to the world around us. Whereas on the System 2 might be what you would associate more with planning the moves when you're playing Go, or when you need to think through some explicitly think through some sets of alternatives. And so arguably we need both system 1 and system 2, because system 2 really generalizes much better than system 1. And yeah, okay, so it's also useful to remember that the online solutions we compute with MPC, they're time indexed versus state indexed on the reinforcement learning side. That the time index can actually be very useful for many movements. And so if you know, this notion of muscle memory or chunking of motions, one can actually imagine that having some kind of time indexed memorization of what's needed for a particularly fast sequence of motions is actually a really useful framework, as opposed to needing to get feedback at every point in time. So yeah, maybe one of the traditionally the biggest distinctions is model predictive control. Because you're doing some kind of optimization on the model, you need to have access to the dynamics model. Whereas in principle, on the reinforcement learning side, you just need to run your simulation forward in time to collect data, to experience data to learn from. And just something I've noticed over the years is, yeah, in the model predictive control side, the state typically refers to the state of the robot, and whereas on a nice thing that's common on the reinforcement learning side is basically we can also integrate our world perceptual model into the state representation, and so that will provide some advantages in terms of flexibility in the world. So just before I get on to showing some actual examples of how in my group we've experimented with MPC and RL, so I just want to point out that just the number of intersection points between MPC and RL. So in both cases, the reward design matters a lot, and so myself and my group, we spend a lot of time looking at people's reward functions for any kind of optimization problem, and getting these right is a non-trivial and maybe underappreciated aspect of making both of these methods work. Both these methods, they will get stuck in local minima. I wish this was more discussed in papers, and it's maybe in part related to reward design, but you know, there's any number of practical you know, tricks, quote unquote, to deal with issues of otherwise avoiding local minima. And so at some point you'll do warm starts of your optimization. The optimization might explicitly include a reference trajectory of some form. Might include some form of curriculum where you start with easy versions of the problem and move towards harder versions of the problem. And so that's something I'll be spending time on today in the rest of the talk. And reward shaping. So again, there are often many terms in the reward function that are used to make the problem easier to solve or that regularize it in some fashion. So another shared aspect is basically just having some notion of a differentiable model. So no matter what you're trying to optimize, you want to follow some kind of gradient typically to solve the optimization, unless you're using some kind of population-based method, and even that is in effect some zeroth order approximation of a gradient. So yeah, so in the MPC side, we typically assume we have some differentiable model of the dynamics, and on the in reinforcement learning, the updates happen via the you know, differentiable models of the policy and value function approximations. So and then yeah, so for both of these methods can take advantages of domain knowledge for simplified models or action spaces and various design features. And they both require some significant expertise to really get good at using these techniques. Lastly, so yeah, there's ways of if I have multiple MPC-based solutions, like we can then turn those into use those as supervised learning of some form to actually produce a directly predictive policy. Similarly, if I have a good existing policy that I might want to, and I might want to fine tune that solution using trajectory optimization, then that provides a path to move from a reinforcement learning policy to help, in effect, warm start an MPC solution. And then one last point of connection is often on the MPC side, we need to have some kind of a terminal cost to use for the end of our horizon, and of course, so that begins to look a lot like a value function in a reinforcement learning policy. Okay, so these methods really, despite being fairly separate in the literature, they really share in any number of things. Okay, so I'd like to just walk you through just a variety of recent work from my group. I won't be going into much of the math. My goal here is really just to give you to comment a little bit on some of the specific features needed to make these that we found to really make these methods work in practice. And so I'll start with maybe the with the 2020 paper, which represents tackling using MPC to learn motions for monopeds, bipeds, and quadrupeds. And so let me just walk you through walk you through this method. So here the basic goal is to use multiple levels of abstraction when setting up the model predictive control method. And so and this is to deal with the difficulty that if right from the start you use a full dynamics model and try to apply model predictive control, then that's difficult because there are many local minima if you start with the wrong initial guess, and it's also time it's also intensive, compute intensive, and so that if we want it to run in real time, we'll often resort to working with a simpler model. And so that's what we'll do here. And so there's actually three models here. So the first is basically a inverted pendulum on a cart model. So that's represented by the center of mass here and the cart. And so if we have some desired speed and trajectory, we can first optimize for the path of the cart for this inverted pendulum to follow this trajectory. Given that, we can then begin to plan footsteps that would support this center of mass trajectory. And then the next level is to move away from the inverted pendulum on a cart and towards the centroidal mass model. And so at this point, we consider the body that, this is the classic potato model where the dynamics is simply modeled by the center of mass and also the angular position of the body and as well the linear velocity and angular velocity of the body. So with this single rigid body abstracted dynamics, our goal will be in part to compute the ground reaction forces over time to make this center of mass model actually follow the center of mass model that we want to see over here that was computed for the earlier inverted pendulum model. So this is adding on additional detail. And then lastly, we want to actually change this to a full model. And so in this particular work that I'm showing you, this will not be a fully dynamic, this will not be the product of a full dynamic simulation. Instead, we're going to use an approximation to that. So we're going to use inverse kinematics along with some version of momentum to keep consistency between the original frames. And as you see the results that I show you, just remember that the final step of this is actually not. We haven't yet taken the step of mapping this to a fully physical simulation, and so there exists some other ways of doing that, but we haven't really looked in detail at that for this particular work. But one of the reasons why I wanted to mention this is that one of the things that we will do in this work is to be able to, given enough example data from this part of the optimization, what we're going to do is actually just learn a solution that goes directly from the center of mass model with footstep locations and directly predicts both the ground reaction forces and this trajectory, as well as predicting the full body motion. And so given enough data from collected from using these optimization components, we can then just simply learn something that maps directly from this component of this version of the solution to our final version. So this is what this and so that learned mapping really helps speed the optimization part, because the inverted pendulum optimization is actually very fast to run in real time, and what takes the most time is that remaining part. And so that's where this is being replaced by a complete prediction. So that prediction is actually running. It runs one motion cycle at a time for the quadruped, and then for the biped, it actually runs one. It looks ahead one and predicts ahead one physical step at a time. Okay, so this is an example maybe of how we can, in some sense, we already have some kind of a hybrid, right, between a pure model predictive control solution and really what's starting to look like a policy, in that we've cached the result of the model predictive control solution, and we say, okay, great, we know what the solution will look like because we've seen enough similar motions before, and we can now just directly go on to predict the remaining part. All right. Let me move on to, okay, so we can provide some additional with the momentum mapped inverse kinematics. We can provide some desired style information so we can bias the human poses towards certain preferred poses. And so with that in place, we can get some more natural motions. We can also actually, during the footstep placement optimization, we can also actually use a population-based method for that particular component of the search. And so here is where so there is an underlying classical model predictive control method. Only when we're actually searching for over the subspace, over the space of foot space solutions, we can actually search over various discrete configurations, and we can do other things. The classic, the nice thing about model predictive control, of course, is we can change the physics and immediately see the resulting adaptations. Okay, so that's one form of MPC and learning that we've had some experience with. This is I'll now move on to this more recent work, and so we've always been really interested in the stepping stone problem. So this is, we want to be able to walk on complex kinds of terrain, and so in this case we're really going to just adopt a reinforcement learning framework and working with the full dynamics in a reinforcement learning based setting. So and so we want to be able to do dramatic motions like this. I highly recommend watching the videos you can find online for this is a team in the UK called Storer Parkour, and the things they can do are just amazing. And so the question is, what how can we learn to this kind of very flexible locomotion? Okay, so for our human model, this will be it's a humanoid model based on reasonable torque limits and mass distributions. It'll be driven by 21 internal torques. So that's our action space. We're going to look ahead. It's going to look ahead 2 steps. Okay, and so So it will be told your next step should ideally be here, and the following one should be here. And we got a reward function, just to give you some details for this. It's going to reward forward progress and energy. It will also be rewarded for making contact with the target step and how close you step to that target location. So that's kind of a one-time bonus you get on each step. To get it to look correct, to look reasonable stylistically, it will be rewarded for having an upright posture. And we're going to impose some we're going to impose a symmetry, a soft constraint on the policy, so that the policy prefers to symmetric motions. And then lastly, we're going to encourage it to not slam into the joint limits, and so there'll be one last term there. So then you might just try this on an environment where you're giving it some steps, and we apply a traditional policy gradient reinforcement learning optimizer. And so in this case, it's simply PPO. But now, so the challenge is that basically, if you give it step sequences, if you begin by the arbitrary step sequences that you'd like to solve, the problem is really too hard, and so basically it fails. And so what we do in this work is we introduce a curriculum for generating the sequence of steps. And so this is like your coach that basically will ask you to practice different step sequences based on some knowledge of your current capability. And so intuitively, what we're trying to do here is really obvious. So if you're learning something new, you should practice motions or that are neither too difficult nor too easy. And so because that will allow for the fastest learning progress. So what this, and so the question is, how do we define this in terms of a curriculum? And so in this work, we really just experiment with 4 different curricula. So the axes on this abstraction, let me just stop this. The axis on the abstraction represent the parameterization of the steps. And so you can, for example, we can imagine the horizontal axis here being the change in step height, or maybe being the change in step distance. So this might be a step, turns to the left and turns to the right, and so with straight being in the middle. And perhaps the vertical axis is the step height. So by default, we could just sample all steps, all future steps equally. That's a uniform sampling baseline. But now what you might want to do instead is begin with steps that are just regular steps that walk forward. So they're not turning left or right, and they're neither going up or down. And then slowly begin to introduce left turns, shallow left turns and right turns, and small steps up and down. And then gradually expand this. And so we call this the fixed order curriculum, where we've specified this expansion procedure by hand. You could also imagine like a fixed order boundary curriculum where you only focus on the new steps that have been introduced. And so because so what this does is it basically says, you should no longer bother trying to learn walking on the straight ahead flat steps, because you already know how to do these. But this risks the possibility that you actually forget to do some of the easy steps. And then lastly, we have kind of a moving away from the hand specified versions. We have an adaptive curriculum where basically we build a model of how good your current policy is at doing various types of steps, and we come up with a model that generates steps that are neither too easy nor too difficult. And so so that's actually what we will do. And so it turns out that curricula 2, 3, and 4, they all work fairly well, and that's really what you want to do to learn a rich variety of steps. So this takes about 6 hours to compute once you have it all appropriately tuned on let's say a 12-core machine. And so yeah, so then this is crossing really large steps, walking up steep steps. And again, so there's no motion capture data involved here. So in this sense, it's trained from using a pure learning objective. We're showing kind of the limitations with some of these examples here. But yeah, so this is yeah. So what's exciting here is that you really can deal with a really wide variety of scenarios, and so we can include step tilt in these scenarios. And we can also run the same pipeline for this is running with the Agility Robotics simulator for CASI, and so this is running with an accurate dynamic model for CASI, and doing a variety of crazy motions. And so again, this is all working with the two-step horizon. So if we can tell it where to step, that means we can also walk on variable terrain. So by just hallucinating some virtual steps on the virtual terrain, and so these characters can really walk up and down and on all kinds of terrains. And this is what it looks like with an alternate dynamics model or robot or character run through this same learning pipeline. You can get this thing to run. So this is kind of or jog. So this is what this looks like for the humanoid, and we can tell that there's also ways to have it to learn how to start and stop. So this is kind of exciting, right? Because they're in some sense, it is doing some kind of planning for its center of mass, and only that it's all implicit, right? Because this is all learned with the full dynamics. It does actually make use of its arms. So here in this particular run, we've actually disabled the control over the arms, and so in this case you'll see it falls more often, and so it is actually also using its arms to maintain balance. And you can get this thing to this is it's doing, I think it's doing small leaps, and so this is again, this falls out from the curriculum, which is asking it to do larger and larger steps, and so we can see some sort of progression from walking steps to leaps, and so that's pretty exciting. We don't yet do full jumps or side steps or sharp turns. There is basically we're telling it where to step. We're not telling it the step timing, but we are telling it where to step. And so we have yet to build a footstep planner on top of this. Actually, we've given this some thought, but it's actually not that obvious to us to how to nicely extend this framework to quadrupeds, which is a little bit surprising, and so maybe we just need to give that some more thoughts. But I just wanted to be frank about the limitations here. Okay, so I'd like to briefly move on to other ways of learning using less pure objectives, and so another way to learn is to imitate from existing data, right? And so this work is not from our group, but this is from a collaboration between Google Research and UC Berkeley by Xubing Peng and colleagues, and so I really like this work. So this is taking actual dog motion capture data and then mapping that onto a in this case a Go robot, if I remember correctly, and so its goal is to imitate the given reference motion, and then and training reinforcement learning using this imitation objective. And then there's also a challenge here in terms of getting this to work on a real robot. And so if you look at the videos in the middle, on the top and bottom rows, if you just try to map this directly without any adaptation, there is still some additional thought you need to do to sim to real. And so in this paper, they deal with that in part by using randomization. And so in recent work, also to be presented at ICRA this year, is we wanted to look a little bit more carefully at the role of randomization in sim to real transfer. And because if we're going to be relying so heavily on simulations, we should really understand when that will cause a problem, and if it does, how to fix that. And so the interesting thing here is that, well, okay, so typically the process might look something like this. This is you as a designer. You get your robot into the lab, and then the first thing you might do is build a simulation of it. And so you extract what dynamic parameters you can from your robot. You run that on your simulator. You learn some policies. You try to run that on the real robot, and let's say it fails. And so or you observe whether it succeeds or fails. And then somehow you want to then change something so that the sim to real works. And so the question is how to go about this. And so one approach is to, a first go-to reflex is to say, okay, maybe we didn't get some of the parameters exactly right. Let's try to add a bit of randomization to everything. So randomization means that we're training the policy not only for one specific robot configuration, but also for a robot that's slightly heavier, slightly lighter, with little bit more friction, with a little bit less friction, and that if that policy is robust to those variations in parameters, then that will transfer better to the real world. Now, what we're going to propose in this paper is basically just that to be a little bit careful about just always resorting to randomization, just because it's always better to actually understand what the true design issues are that are preventing you from transferring from simulation to real. And so our motivation here is that in much of our in some of our experience, randomization basically isn't necessary. So if you do have a reasonable model of your dynamics, then we are able to get successful sim to real transfer of policies with basically no randomization. No dynamics randomization applied when training the policy. And so these are some different gates and just on the like you go. Okay. And so we did this earlier as well for CASI. And so these we trained using deep reinforcement learning a variety of gates for CASI. And again, that was without randomization. So there seem to be some differing stories here, right? So there's one paper that says that we needed randomization to get it to work, and there's other experiments that basically show that we can get things to work without randomization. And so actually the notable thing about these two papers is that they're actually on the same robot, and they're both doing some kind of imitation-based learning. And so what the question is, what's the real issue that at play here? So one thing that we noted is that so there's a few things. One is that if you train without a state estimator that gives you some estimate of the velocity of the velocity of your robot, then indeed you will have problems with sim to real. Okay, so this is a policy that trains correctly in the simulator. So the state description does not have access to the velocity. It has access to all the proprioceptive information, but not the no overall state estimate of the velocity. And so that actually does not transfer. And also, if you train with so both of these policies for the above papers are producing target actions, are producing target positions, target joint angles for PD controllers, and so there's a gain parameter that you need to decide on, and so the selection of that gain parameter, it turns out to really affect sim to real for us. Okay, and so the randomization can be really useful for other issues. So if you don't know how much delay exists in when running your robot, then that can be an issue. And so basically, here we're actually adding artificial delay to the system, and so if we train without randomization on that delay, then the transfer is poor. And so here we are training with not only with delay but with randomized delay. And so basically, if you're unsure about the delay that's actually in your control loop, then it's definitely worthwhile training with randomization in that delay. So there are cases where randomization can save you. Okay, so those were just some practical insights on dynamics randomization, and just being a little bit cautionary about always resorting to it as a default trick to help enable sim to real. Okay, so just maybe one last work that I'll briefly go over, and this looks at using reinforcement learning for centroidal models. And so model predictive control is often applied to centroidal models. Maybe we can also apply reinforcement learning to centroidal models. Typically reinforcement learning is applied to the full model, and we collect data using that. And so we can do the same thing for a centroidal model. And the action space here will actually simply be the linear and angular accelerations of our centroidal model, because that's the space of things which we can control for a centroidal model. And so the question is, what can we do with that, and is that actually a reasonable thing to do? So the assumption is that we're going to start off with fixed gate timing and massless legs. And so this centroidal model is very fast to simulate and easy to parallelize, which means that it's very easy to run hundreds or thousands of these on a GPU together. So it's very fast to collect data on this, and the reward design is really simplified with a centroidal model, so we can deal with accelerations, for example, and smooth body motion. So this is what this will look like. We're going to learn a reinforcement learning policy. It gets access to the current foot positions and this kind of known foot phase timing. And it's going to request a desired body acceleration, and we're going to put that on top of a QP solver, so quadratic programming, to actually, given desired body acceleration, it will actually generate the ground reaction forces that best achieve this ground acceleration. And then a last key part is foot placement. So we're going to use basically a Raybert style foot placement heuristic, so that when a foot goes into its airborne phase, the default foot placement will be based on both a terrain map and a Raybert foot placement heuristic, and I can go into more detail on that if you have questions on that. So this is the centroidal model and reinforcement learning policy. So it implements that abstraction. And then to actually make it work on the real robot, we're going to use Jacobian transposes to actually produce torques. And then we're for the foot placement, we're going to use some form of basic spline curve and trajectory tracking to have to generate the foot swing trajectories. Yeah, so you can really get this to actually work fairly well and to adapt to there is the reinforcement learning policy really is essential to adapting the requested body accelerations to match both what the terrain allows for and what the body dynamics allows for. You could also do walking across a balance beam configuration here. So again, it's seeing this terrain constraint, and it's trying to manage. There are some oscillations in the body position, and so it's trying to manage those over time to successfully walk across the terrain. Could also do something like basically a two-legged balance on a quadruped. So that so it is needing to manage the angular accelerations in a way that in the same way that an acrobat manages its configuration in order to stay balanced over time. And so the nice thing is that this will just fall naturally out of the reinforcement learning framework. And this does actually transfer to the real world. And so again, this is a mixture. It's a mix of offline reinforcement learning using the simplified model, and then online it's running these. It's still running the QP and using Jacobian transposes, etc. And so and using these learned body accelerations. And so it's surprisingly robust for sim to real. And so yeah, I just want to. This is an example of using some kind of a QP hybrid mix of RL on a simplified model with a more traditional model-based approach underneath. And so we're interested in further pushing this kind of approach. Okay, so I'm basically almost done. This is it is also possible to get something like pure reinforcement learning to learn to discover something like high jump solutions. And so this is actually work we're excited to present at SIGGRAPH 2021. And so here, this is a completely physics-based simulation from beginning to end. The motion from the takeoff state to the end is completely synthetically generated, and so I guess the point I want to emphasize here is that it is possible to use reinforcement learning to discover what we would normally think of as very difficult novel motions to discover. I'm happy to point you to the paper, but it is exciting to see that reinforcement learning can be used to discover strategies like the Fosbury flop. And there's a bunch of caveats on that, but I'm happy to answer those in questions. So just to wrap up, as I'm running out of time, if there are people in the audience just getting started with model predictive control and reinforcement learning, be aware that both require significant expertise to get it to work well, and that coexistence of multiple approaches is actually a good thing. And so when solving a problem, I don't think that an MPC solution needs to prove itself better than an RL solution, or vice versa. I think there's ample space and need for a diversity of approaches for these problems. Arguably, you could just view RL reinforcement learning policies as just caching good solutions, right? And so basically, the most basic version of learning to solve MPC problems is if you just memorize the solution for every given state, and to some extent that's exactly what a reinforcement learning policy does. And so I think the interesting question comes when there's still a benefit to search, right? And so if you need to search over possible foot placements, then a default reinforcement learning policy can't does not directly support that. And so this is maybe analogous to AlphaGo, where basically you can learn a pure policy to play Go or to play chess, but it actually will not be as good as a policy which combines that policy with additional search. And so legged locomotion should also maintain both these aspects, where I think we need to cache some aspects of the solution and just pre-compute them, and other aspects will always need to be reserved for online search. So arguably, this should happen in some kind of learned latent model, and we can do online planning in that space. Yeah, and so the maybe the most common theme in the work that I've shown you is that I believe that there's a huge amount of scope for learning based on curricula, and so a curriculum lets you gradually transform a solution from the easy examples, easy instances of a problem to the more difficult instances, and so that means that you avoid having to ever really having to learn from scratch. Yeah, and that even in the reinforcement learning setting, action abstractions can actually play an important role. And so I still think we need to see more work on what good action spaces are, and ways of abstracting actions that we can learn from. So having said that, let me stop there, and I'd be delighted to take any questions. Thanks.
Thanks a lot, Michiel. It was a really interesting talk. So just to repeat again, if you want to ask a question, you can either use the hand raising feature of the Zoom, and then I will call your name and you can ask your question directly, or you can just write it down in a chat session, and then I will ask for you. I think we have a couple of questions here. I can start with the first one. So the question here is, first, is the centroidal model and single rigid body are equivalent if we have a massless limbs? Which I can answer yes. And then how can we get more natural looking motion without using these mockup references?
Okay. Right. Okay. Well, okay. So first, yes, the centroidal models that we use both in the work that's on screen here and the previous work I showed. Those they do all have massless legs. Yeah. And then yeah. So for making motions look more natural. So that's where I think one thing that I didn't show in the case of the in the case of the high jump, for example, one thing that is also happening here is that we are using something called that we call a pose variational autoencoder, and so basically we basically train a pose generator. We come up with the latent space for poses. So it's some reduced dimensionality, reduced dimensionality space for human poses that we basically train on a large motion capture database that includes all kinds of motions, but does not include high jump motions. And then so you'll see in this paper it is actually important to sample from an action space that produces that comes from that pose variational autoencoder. And but yeah, fundamentally that's just it is some kind of a model of what reasonable poses can and should look like. In the other work, sometimes you can just use a surprisingly small number of terms to have this fall out naturally. And so for example, in the stepping stone work, if I can just go to the slide that talks about the objective functions here. So here the here there is no motion capture data, and so literally the terms that encourage are that the desired motion are, again, we tell it of some notion of symmetry. We encourage the body to be upright, and then the rest really does just come from energy and other and falls out of the optimization. So interestingly enough, like for this particular humanoid model, it does not use its arms to balance. So it prefers to keep its arms tightly to its body. Whereas for the green monster character, it when it's doing the bigger steps, it really does like to use its arms to help maintain balance. And so and in that case, you could argue that it actually seems fairly natural, but for whatever definition of natural you might want. I hope that answers the question.
Yep. Right. Okay, the next question goes to the learning the centroidal model and whole body trajectory. So you mentioned there that it's difficult for quadruped robots to do this. The question is, do you know why, or do you have some clue why this is the case?
Oh, okay. Let's see. Yeah. Okay. There's so it's really for the stepping stone work that that we haven't yet been able to extend that to a quadruped, and so in part that's due to our particular setup of the problem. So our setup of the problem, we basically tell it where to step next, and so yeah. So if this was a quadruped, yeah, I suppose we could tell it where each and every leg should go next. Although, I think for a quadruped it would work better if it was trained just on variable terrain, and we slowly increase the difficulties of the difficulty of the terrain. But so for our particular case, we were really training on these very isolated steps that are kind of hanging in space, and so if if I have a quadruped here, it's not as obvious as to how to specify some kind of a feasible plan, some kind of a feasible footstep plan, at least in our current framework. For doing this, so I do think with some additional effort that we could get some version of this working for a quadruped, and yeah. So I think that covers the question. But for the other for this work, here we are. For this work where we are actually predicting the full body motion, there we do use this for a quadruped for this particular case without issue. So
the next question is regarding the consistency of the RL policies, especially since you brought up that sometimes it forgets to walk on a simpler terrain, and something fails in stepping stone scenarios. From an RL perspective, beside randomization, where do you think we can look for better feasibility and stability guarantees?
Okay. Right. Okay. So maybe there's two questions in there. One is do you need to worry about forgetting, and the second one is about stability and guarantees. So for the first question, actually, it turns out that you don't need to worry that much about forgetting. So in number 2 here for the fixed order version, there we do continue to practice the easy steps, and whereas the fixed order boundary version, there we stop practicing the easy steps, and we only practice on the edge configurations. And so it turns out that there's actually not that much difference between these two cases, and that if you can always do difficult steps, then then effectively interpolating back to easier steps is actually not that critical. And so so the ideal scenario of adaptive is actually, the adaptive doesn't do that much better than it does a little bit better, I believe, than the fixed order and fixed order boundary, but it doesn't do that much better in some kind of critical way. So the key take home here is you need some form of curriculum, but forgetting was not a really significant issue for this particular problem. For the question of stability and robustness, yeah, no, that's something that I'm also very interested in. I think having some policies that are aware when they're going out of distribution and some form awareness of some form of uncertainty, I think that is really important. And currently the most common approaches are to use some kind of ensemble policy, or you could even use like an ensemble value function, and so that when you're really going out of distribution, you're hoping that you know when you're going out of distribution, because either you learn multiple policies for the same task and you see if they agree or not. That's kind of the most obvious way. But yeah, it is difficult to provide any guarantees, right? Because here, like for any successive sequence of 2 steps, each step has 6 degrees of freedom, right? Because we're dealing with step tilt as well as 3D position. And so by the time you take 2 steps in a row, that's like a 12-dimensional space. And so providing hard guarantees on which parts of that 12-dimensional space your policy can effectively deal with, and where it breaks down. Yeah, that's I think it'll be difficult to provide true hard guarantees, but I think we will see better models of confidence and kind of being able to provide soft guarantees. And that the easiest version of that is just using ensembles. But yeah, more work needs to be done for sure.
Mm-hmm. Okay, so we're a little over time, but we have 2 more questions. If it's okay, I go then.
Sure. Yeah. Up to.
So the question here is, how do you do the mapping between CDM and whole body dynamics, and is it generalizable to any morphology of this robot, I assume?
Oh, right. Yeah. Okay. Yeah. Okay. So this is based on the on this momentum mapped inverse kinematics, and so it is basically a version of inverse kinematics that takes some additional effort to make sure that overall the overall momentum is preserved. Is it generalizable? Yeah. I mean, I think, yeah, I think it could generalize to other forms of robot morphology, but I think the real question is still to be tested with this particular work is ultimately we'd really like some last true inverse dynamics, followed by a true forward dynamic simulation mapping, right? So and to see. To really test to see how robust that map, to see whether this mapping actually supports whether it truly does support up mapping to the true physical model, right? Because the true ground truth is will it work with the full body dynamics? And so in this particular case we did not do that last step, and so. But there have been a variety of forms of that last step done by any number of model predictive control approaches, and so we're optimistic that some form of this would work and extend to the full to actually working on the full dynamics model, but we haven't tested that yet.
And our last question is regarding, I think, this randomization. The question is there any observation to show a trade-off between robustness and performance for the regarding randomization of the dynamics? And if so, does it motivate to spend time to have a more accurate model and reduce the effort for the randomization?
Yes, yeah. Okay, so we talk a little bit about this in that paper. Yes, absolutely, there is a trade-off, right? So if you randomize unnecessarily, then your policy will become unnecessarily conservative, and so absolutely, there is a price for excessive randomization. And so that's also why we argue for apply randomization with caution, and just make sure that that your randomization is being applied for the right purpose. Just because if you randomize with respect to body mass or something, and you're hoping that helps you deal with a if the real problem is some kind of is your latency in your feedback, and then you're hoping to tackle that by randomizing the mass and some joint frictions, well then maybe that's not helpful, right? And so of course that assumes that you have some kind of a way of access of trying to discover where the real mismatches are, and so there's no formulaic answer for that. That's always challenging. However, I do think that feedback latency is definitely a common source of problems when mapping sim to real that we found. And so and so we do some experiments that go to show that in with this particular work. But
very nice. Okay, I think with this is end of our questions. Thanks a lot, Michiel, for the talk and great discussion, and thanks for our audience. And now this would be the end of the session.
Great, yeah, my pleasure. I look forward to the other talks in the workshop. Take care, all.